Hi folks, we're going to take a look at an example of sketching the graph of a rational function. Okay, so step number one is going to be to factor both numerator and denominator, see if there's any simplifying, and then we're going to use that to analyze the function. Okay, so I see a cubic with 4 terms in the numerator, so I should be thinking of grouping, but if I take a quick look at the first and last 2 terms, I notice that grouping unfortunately is not going to work there. So here we have no choice but to use the factor theorem. So I'm going to be looking at my factors of 2. So let's say I call this g here, so let's check g at 1. So 1 minus 1 is 0, minus 3 is negative 3 plus 2, not equal to 0. Okay, so let's test out g at negative 1. Okay, so here we've got, becomes negative 1 minus 1 is negative 2, plus 3 is 1 plus 2, not equal to 0. Okay, so let's try g at 2. Keep going until we find something. So here we have 8 minus 4 is 4, minus 3 times 2 is 6, which is negative 2 plus 2. There you go, that's equal to 0. So we know that in my numerator I've got a factor of x minus 2. I just need to find the quotient of the division between this cubic and the factor x minus 2. So because I'm dividing by a linear factor, I can use synthetic division. So let's go ahead and do that. Okay, so bring down the 1. 1 times 2 is 2, so negative 1 plus 2 is 1. Times 2 is 2. Negative 3 plus 2 is negative 1. And just to check, to make sure the remainder is 0. So negative 1 times 2 is negative 2, and 2 minus 2 is 0. Okay, so looks like we did that correctly. So this becomes x squared plus x minus 1. Okay, and the denominator factors very easily, just x minus 1, x minus 2. Okay, so here I do see some nice stuff because I see the x minus 2 in the numerator and denominator can reduce. Okay, so here I'm left with x squared plus x minus 1 over x minus 1. And of course these expressions are only equal if x is not equal to 2. Okay? So a couple of things. We have to interpret what this means in terms of the graph. And I also notice, unfortunately, that numerator is not factorable. So we'll talk about that in a second. But again, when we factor out a linear factor from both numerator and denominator, this implies that we're going to have a whole at that x value. Okay? Now, let's keep in mind why that is. It's because this function and this simplified one are identical in every way. The only difference is that this one is defined for x equals 2 and this one is not defined for x equals 2. Okay, so we essentially just have to remove this one point that occurs when x is equal to 2 from that function. Okay, so now we can go ahead and start analyzing it. So we'll start with our domain here. So x is an element of R such that, well, let's see what x can't be equal to. So remember, you always have to go to that original function. X can't be equal to 1 or 2. Okay, now we can look for our x-intercepts. So here we do have to do a bit of work because the numerator is not factorable. But we can still determine when it's going to be equal to 0. So we can use the quadratic formula for that. X equals negative 1 plus or minus square root of 1 squared minus 4 times a, which is 1, times c, which is negative 1, all over 2 times 1. Okay, so this ends up giving us negative 1 plus or minus 1 plus 4 is 5, root 5 over 2. Okay, now these are the exact x-intercepts, but of course since I need to graph this, I'm going to look for approximations here. Okay, so let's see what we get. Try this side. Okay, so here we've got negative 1 plus root 5, okay, and then divided by 2. So we've got about 0.62. And then the other one will be negative 1 minus square root of 5, and then divided by 2. So about 1.62. Okay, honestly, I could have even worked with just 0.6 and 1.6. Okay. Let's go for the y-intercept. So again, I can actually work with either function here. Notice it gives me the same amount. I put in x's everywhere here, and I'm just left with 2 over 2, which is 1, or here I put x equals 0, and all I'm left with is negative 1 over negative 1, which is still 1. So there's our y-intercept. Okay, so our vertical asymptotes. Okay, so because this is already simplified, I can just read off the vertical asymptotes by looking for the 0 of the denominator. So here we have a vertical asymptote at x equals 1. Okay, so let's now look at determining the sign of this function, where it's positive and negative. So again, if you prefer making a chart, that's perfectly fine, but I like using a nice simple number line here. So where do we actually have to determine the sign of the function? So here we've got our zeros and at our vertical asymptote. So here we got, oh sorry, I just realized here this was supposed to be negative 1.62. Okay, so here we've got negative 1.62, then we've got 0.62, and then we've got 1. Okay, so we have 4 intervals to check. So let me start with something less than negative 1.62, so let's put in negative 2. Okay, so negative 2 squared is 4, then minus 2 is 2, minus 1, so we got something positive over negative 2 minus 1 is negative. So the result is an interval of negative y values. Okay, in between here, well, we actually have x equals 0. We've already calculated the y-intercept, so we know this has to be positive. No need to recalculate it. Here in between, well, I guess we could take 0.7. Okay, now looking at this quadratic, you can probably figure out on your own, maybe by drawing a little picture, whether 0.7 should give you a positive or negative answer. But just to be sure, I'm going to calculate it. It's not going to take much time. So 0.7 squared plus 0.7 minus 1. Okay, there we go. We get a positive number. And then 0.7 minus 1 is a negative number, so over negative. So the result is negative. And then when I put something like 2, something bigger than 1, I get 4 plus 2 minus 1 is positive. And then here 2 minus 1 is still positive. So everything's positive there. Okay, so now we've got our behavior in terms of the sign of the function. And the last thing we're going to determine is going to be the end behavior. Okay, now because we have a quadratic over a linear, we should know that it's going to approach positive or negative infinity, but it's going to do so along a linear oblique asymptote. And the way we determine what the equation of that asymptote is just by division. Okay, in this case here I'm dividing by a linear, so I don't need long division. So I've got 1, 1, negative 1. Okay, and I have to divide that by x minus 1, so we'll put a 1 there. So here we got, bring down the 1, 1 times 1 is 1, 1 plus 1 is 2, and I actually don't care what the remainder is here. The only thing I care about is the quotient of this division, and I see that I have an oblique asymptote of y equals x plus 2. Okay, so now we have all the information we need to sketch the graph of this function. We just have to put it all together. So one thing is to determine the scale that we're going to use. Okay, so I look at my x values, 1.62, negative 1.62, pretty small values, and since I've got some fractions, it might be a good idea to actually go up by 2 boxes at a time for each unit. Okay, now for the y values, well, I have a y-intercept of 1, which is pretty small, but I look at my oblique asymptote and I see that I'm going to have to take y equals x and move it up by 2 units. So I think I might just stick with going up by 1s on the y-axis, and I think I'm actually going to draw the x-axis a little lower just to make sure I have enough room on my graph to draw this. So these are the kinds of things you have to look at, because if you don't choose a good scale, it might be very difficult to actually draw that graph. So here, I think it'd be okay to just put this right down the middle. Okay, so I said I was going to choose 2 boxes for 1 unit here, and here I'll go up by 1 unit per box. Okay, so now we set up our structure. Let's put in the things we know. So we have x-intercepts at negative 1.62, so 1.62 0.62, so somewhere there. Okay, then we've got another one at 0.62, so that'll be somewhere there. And then we have a vertical asymptote at x equals 1. So let me indicate that. Okay, we have a y-intercept of 1. Put that there. And now we have an oblique asymptote of x plus 2. So think of y equals x. So it goes from 0, 0 to 1, 1, except we're moving everything up by 2 units. Okay, so the y-intercept will be here. Okay. Okay, so try to do as nice a job as you can there. Okay, so now we've got the structure of the graph. If we use the sine, even though you should be able to figure some of this out without actually looking at the sign of the function, but I see that we're going from a negative to positive. So negative, and then in this whole interval we're going to be positive, and then it goes back down to negative. So that tells me how the function behaves near these asymptotes. So it's going to approach the oblique asymptote as it goes to negative infinity. It's going to come up and go to the y-intercept, then it's going to have to cross at the x-intercept, and so this means it has to go to negative infinity as we get closer to the vertical asymptote. Okay, now let's see what's happening to the right of 1, and we see that it's always positive. And this is a tough one because where exactly do we draw this? I know that if it's positive, it's going to have to go to positive infinity here. I know it has to follow the line to go towards positive infinity as in behavior, but where exactly to draw it? And the fact is we don't have the tools right now to really get a good sense of where it should go. So as long as you draw something that's reasonable at this point, okay, so something that follows the oblique asymptote and then follows the vertical asymptote, okay, that's acceptable. Okay, now if you remember in class, I suggested you do a little something. I suggested that you indicate near your graph when there's a hole. Now it just so happened that my screen shows that hole, but imagine if my screen was like this, I might miss it altogether. So again, I'm going to reiterate that little hint about finding holes. Just write it near your graph so that you're going to see it as you're drawing your graph. And so now what we have to do is we have to find x equals 2. Okay? And then wherever we've drawn our y values, just make sure you indicate that there's a hole there. Okay? Again, if you miss that, it means you haven't really drawn this function here. Okay? Or what you've done is you've drawn this function, but you haven't incorporated the fact that there's a restriction. Okay, so I want to suggest that you follow this order, okay, so that you don't forget anything, that it becomes an algorithm, okay, and that before you start to draw anything on your graph, make sure you set up your whole structure, which means indicate your x-intercepts, your y-intercept, any asymptotes that help you with end behavior or vertical asymptotes, and just make a note of where you might have any holes.